Welcome back to this second introductory lecture on proof techniques. In this second segment, we will discuss the technique called proof by contraposition. We still assume that we are trying to prove a theorem of the form P implies Q. To prove this conditional, this technique suggests that we instead try to prove its contrapositive, not Q implies not P. This is a valid proof technique because remember we proved that a conditional P implies Q is logically equivalent to its contrapositive not Q implies not P. Therefore, proving one is the same as proving the other. When the earlier proof techniques do not apply to the theorem you're trying to prove, or at least not in an obvious way, the next thing you should consider is trying to prove the contrapositive of that conditional, which may turn out to be easier. And how do you prove the contrapositive? Well, it's another conditional, so you can apply the proof techniques you already know. Now, make sure you convince yourself that if the vacuous proof and the trivial proof did not work with the original conditional, they also will not work with the contrapositive. So therefore, we'll consider using a direct proof to prove the contrapositive. And what that means is we're going to assume the hypothesis, in other words, not Q, or Q is false, and we're going to prove under this assumption that the conclusion not P is true, therefore that P is false. So that is the technique, proof technique called proof by contraposition. And we're now going to illustrate it on the same theorem that we were stuck on in the previous segment. Namely, for every integer n, if n squared is even, then n is even. Since we already realized that the earlier proof techniques do not obviously apply to this theorem, we're going to proceed right away with a proof by contradiction, by contraposition, which is the subject of this segment. Since we're trying to prove a universally quantified statement, we first have to pick an arbitrary integer, let's call it n. Then, in a proof by contraposition, we must assume that the conclusion of the conditional is false. In other words, that n is even is false, which is the same as saying n is odd. So let's assume that n is odd. Now what we're trying to prove is that the hypothesis of the conditional is also false, namely that n squared is not even or odd. So let's start from the definition of n being odd as usual to infer that there must exist an integer k such that n is equal to 2 times k plus 1. How are we going to prove that n squared is also odd? By using the definition, we need to find an expression for n squared. Since we have already an expression for n, we simply square this expression to get an expression for n squared. So what we get by squaring both sides of this equality is n squared is equal to 2k plus 1 squared. Let's just multiply out the terms of this square on the right hand side. Remember that a plus b squared is equal to a squared plus 2 times ab plus b squared, where a is 2k and b is 1. So a squared is going to be 4k squared, b squared is going to be 1 squared, or 1, right here, and 2 times ab is going to be 2 times 2k times 1, or 4k. Now we need an expression for n squared that's of the form 2 times something plus 1. So to get there, let's factor out 2 out of these two terms to get 2 times 2k squared plus 2k plus 1. Now we know that this k here is an integer. Therefore, 2k squared plus 2k is also an integer. So we can use existential generalization to infer that there also exists an integer k such that n squared is equal to 2k plus 1. where the k needed here is this particular integer. Well, that is the definition of n squared being odd, so we can infer that as the next step. Since we came to that conclusion under the assumption only that n is odd, we just inferred the conditional n is odd implies n squared is odd. By contraposition, this means that we also prove that if n squared is not odd, then n is not odd. In other words, if n squared is even, then n is even, which is starting to look like this theorem we're trying to prove. But remember, we're not quite there yet, because here n is universally quantified, whereas here n is a specific but unknown integer. So the last step we need to perform is universal generalization to infer that for every integer n now, we prove that if n squared is even, then n is even. And that concludes our proof by contraposition of this theorem. So to conclude this segment, remember that a proof by contraposition only applies to a theorem that is stated as a conditional P implies Q. This approach tells you that instead of proving P implies Q, you can try and prove it's contrapositive, not Q implies not P. And in particular, you can try to use a direct proof to prove that not Q implies not P. And that is exactly what we did on this example, and that's the general approach for a proof by contraposition. Now, why did we come to the conclusion of trying this proof by contraposition? That's because we couldn't find a direct proof for P implies Q. So it's a general strategy that when you can prove a conditional in a direct way, you might want to try to prove it in an indirect way using proof by contraposition.